310.15 allows feeders to a separate building on the same property, like a garage, to be sized no smaller than the larger of two values: firstly, 100 amps, or secondly, the calculated load for the building. This means you can size the feeders to your garage at a minimum of 100 amps, even if the calculated load is less than that. It is important to note that because the feeder to the garage is a separate feeder, it must also comply with 310.15(3). These sections address several crucial aspects of feeder installation. This includes requirements for overcurrent protection. Overcurrent protection ensures that the feeder is adequately protected against faults and overloads. Proper overcurrent devices, such as circuit breakers or fuses, must be selected and installed to interrupt the circuit in the event of an overcurrent condition. It also specifies acceptable conductor materials. Conductor material refers to the type of metal used for the feeder conductors, typically copper or aluminum. The choice of conductor material affects the feeder's ampacity and resistance. It also covers installation methods. Installation methods encompass the way the feeder conductors are installed, such as in conduit, cable trays, or direct burial. The installation method impacts the feeder's ampacity and protection from physical damage. Finally, it addresses ampacity adjustments. Ampacity adjustment refers to the need to adjust the conductor ampacity based on factors such as ambient temperature, the number of conductors in a raceway, and the type of insulation. These adjustments ensure that the conductors are not overloaded and operate within their temperature rating. Therefore, while you can use 310.15(6) to determine the minimum size of the feeder to your garage, you must still adhere to the requirements outlined in 310.15(b)(e) for separate feeders. This involves careful consideration of overcurrent protection, conductor material, installation methods, and ampacity adjustments to ensure a safe and compliant installation. To elaborate further on each of these requirements, let's begin with overcurrent protection. Overcurrent protection is a critical safety measure designed to protect electrical circuits and equipment from excessive current flow, which can lead to overheating, damage, or even fire. In the context of a feeder to a detached garage, overcurrent protection is typically provided by a circuit breaker or fuses located at the main service panel where the feeder originates. The size of the overcurrent protection device, measured in amps, must be appropriately matched to the ampacity of the feeder conductors. The National Electrical Code (NEC) provides specific guidelines for selecting the correct overcurrent protection based on the conductor size and type. Generally, the overcurrent protection device should not exceed the ampacity of the conductors it is protecting. For example, if a feeder consists of 8 American wire gauge copper conductors with an ampacity of 40 amps, the overcurrent protection device should typically be rated at 40 amps or less. There are some exceptions and allowances for specific types of equipment, such as motors, but the fundamental principle remains the same. The overcurrent protection device must be capable of interrupting the circuit in the event of an overcurrent condition. This interruption should occur quickly enough to prevent damage to the conductors and equipment. Circuit breakers are designed to trip automatically when an overcurrent is detected, while fuses are designed to melt and break the circuit. It is essential to select overcurrent protection devices that are listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories, UL, to ensure they meet safety standards and performance requirements. Moving on to conductor material. The choice of conductor material is a significant factor in electrical installations, as it affects the conductivity, ampacity, and overall performance of the circuit. The two most common conductor materials are copper and aluminum. Copper is widely used due to its excellent conductivity, high tensile strength, and resistance to corrosion. Copper conductors can carry more current for a given size compared to aluminum conductors. This makes copper a preferred choice for applications where space is limited or where high ampacity is required. However, copper is generally more expensive than aluminum. Aluminum is a lighter and more cost-effective alternative to copper. Aluminum conductors are often used in larger sizes, such as for service entrance conductors or feeders, where the weight and cost savings can be substantial. Aluminum has a lower conductivity than copper, so aluminum conductors must be larger than copper conductors to carry the same amount of current. For example, a 2 American wire gauge aluminum conductor is typically required to carry the same current as a 4 American wire gauge copper conductor. When using aluminum conductors, it's crucial to use connectors and terminations that are specifically designed and rated for use with aluminum. These connectors are typically made of aluminum alloy and are designed to prevent corrosion and ensure a reliable connection. Aluminum is more prone to oxidation than copper, so using the correct connectors and applying an antioxidant compound can help prevent connection problems. The NEC provides specific guidelines for the ampacity of both copper and aluminum conductors based on their size, insulation type, and temperature rating. These guidelines must be followed to ensure that the conductors are not overloaded and operate within their safe temperature limits. Now let's examine installation methods, which play a crucial role in ensuring the safety and reliability of electrical circuits. The NEC specifies various acceptable installation methods for conductors, each with its own set of requirements and limitations. Common installation methods include firstly, conduit, secondly, cable trays, and thirdly, direct burial. Conduit is a rigid or flexible tube used to protect conductors from physical damage and environmental factors. Conduit can be made of various materials, such as metal, PVC, or fiberglass. Metal conduit provides excellent mechanical protection and can also serve as an equipment grounding conductor. PVC conduit is lightweight, corrosion resistant, and suitable for underground installations. The NEC specifies the types of conduit that are permitted for different applications and environments. Cable trays are open support systems used to route and support conductors, cables, and raceways. Cable trays are commonly used in industrial and commercial buildings where there are many conductors and cables to be routed. Cable trays provide easy access for maintenance and modifications. The NEC specifies the types of cables that are permitted to be installed in cable trays and the requirements for supporting and securing the cables. Direct burial involves burying conductors directly in the earth without any additional protection. Direct burial is typically used for underground feeders and branch circuits. The NEC specifies the types of cables that are permitted for direct burial and the minimum burial depths required to protect the cables from physical damage. When installing conductors, it's essential to follow the NEC guidelines for the specific installation method being used. This includes requirements for supporting and securing the conductors, protecting them from physical damage, and ensuring proper grounding and bonding. Improper installation can lead to electrical hazards, such as shorts, ground faults, and fires. Finally, ampacity adjustments are necessary to account for factors that can affect the heat dissipation of conductors and their ability to carry current safely. The NEC requires ampacity adjustments in certain situations to ensure that conductors are not overloaded and operate within their safe temperature limits. Common factors that require ampacity adjustments include firstly, ambient temperature, secondly, the number of conductors in a raceway, and thirdly, the type of insulation. Ambient temperature refers to the temperature of the surrounding environment where the conductors are installed. Higher ambient temperatures can reduce the ampacity of conductors because they have less capacity to dissipate heat. The NEC provides ampacity correction factors for different ambient temperatures, which must be applied to the conductor ampacity rating. For example, if a conductor has an ampacity of 30 amps at an ambient temperature of 30 degrees Celsius, but the ambient temperature is 40 degrees Celsius, the ampacity must be reduced by applying the appropriate correction factor. The number of conductors in a raceway can also affect the ampacity of the conductors. When multiple conductors are installed in the same raceway, they generate heat that can increase the temperature inside the raceway. This can reduce the ampacity of the conductors. The NEC provides ampacity adjustment factors for different numbers of conductors in a raceway, which must be applied to the conductor ampacity rating. For example, if 3 current-carrying conductors are installed in a raceway, the ampacity of each conductor must be reduced by 80%. The type of insulation used on the conductors can also affect their ampacity. Different insulation materials have different temperature ratings which determine the maximum temperature at which the conductor can operate safely. The NEC specifies the ampacity ratings for different types of insulated conductors based on their temperature ratings. For example, conductors with a 90°C insulation rating have a higher ampacity than conductors with a 75°C insulation rating. When making ampacity adjustments, it's essential to consider all the factors that can affect the heat dissipation of the conductors and apply the appropriate correction and adjustment factors. Failure to make the necessary ampacity adjustments can lead to overloaded conductors, overheating, and potential electrical hazards. To summarize, when sizing feeders to a detached garage, you can use 310.15, a 6 to determine the minimum size of the feeder. However, you must also comply with the requirements of 310.15, B through E for separate feeders. This includes careful consideration of overcurrent protection, conductor material, insulation methods, and ampacity adjustments. By following these guidelines, you can ensure a safe and compliant electrical installation.